I'm actually not starting exactly where we ended off because I want to take a running start at black holes. So the deal with black holes is, a reason they call them black is because light can't escape from them. So it's dark. Okay. You're fine. The other thing about black holes, I like them because they're kind of a continuation of, I just think it's so awesome because we have a white dwarf, which is really compact. We have a neutron star, which is really, really compact. And then we have a black hole, which is really, really, really compact. And we said electron degeneracy stops the collapse of a white dwarf. We said neutron degeneracy, neutron soup, stops the collapse of a neutron star. And nothing stops the collapse of a black hole. So kind of with regard to, you're like, okay, so what is that stuff over there? I don't know. It's like this kind of strange sort of matter, okay? Definitely not the atoms that we all know and love, which is fine. So the little thing in the center, okay, this object creating the black hole is called the point of singularity. Sometimes I've heard it described as actually not a point, it's more like a ring, singularity. I don't know. But what's important to know is we talked about the event horizon outside of the singularity. Okay, and the event horizon is important to know where it is, because if you go on the inside of the event horizon, you are toast. Okay. So then the other thing, we're going to kind of pick up here. We're almost to, this seems like the last one we did maybe, or maybe one more. Okay.
You got the first part of the second one.
Yeah. Okay, thanks. So Einstein, it's cool because Einstein has his special theory and then his general theory. Special theory of relativity and general theory of relativity. And the dude, he predicted black holes before anybody else did. So basically he said the way the universe works, this should happen. Isn't that cool? So along those lines, he also, in his general theory of relativity, came up with this concept of space, the fabric of space and time. So we talked about this, that actually, and it makes sense, that when you're walking around, okay, there's a spatial aspect to it, but there's also a time aspect to it. Okay, it kind of hurts my brain to think about it. If you think of this room and think of the people coming and going today, think of the people coming and going this month, think of the people coming and going this year. Think about what this location looked like 20 years ago. You know what I'm saying? It was, the space was here, different time. What was it like? I don't know. It's science fiction. Okay. So I added the 1905 because I thought that was significant. The older I get, the more I am into like history. Okay. So in math, they do a lot of they do a lot of assumptions. They basically set the groundwork for the math problem, and then they proceed to do the math problem. They do it all the time. So setting the groundwork for Einstein's theories of general theory of relativity or special theory of relativity, there's two ground rules. So these are ground rules. Okay. We're going to talk about movement. But honestly, here's the deal. Okay, so you guys are sitting still, mostly. Okay, and I am moving. You have a sitting still reference. I have a moving reference. They're different. Sitting still, moving. Your frame of reference, my frame of reference. Okay. So we're going to talk about these frames of reference. So basically, we're going to talk about the difference between going fast, like almost the speed of light fast, okay, versus somebody whose frame of reference is sitting still. So here's the deal. If I have, and we're going to deal a lot with time, and we're going to deal a lot with length, and we're going to do a little bit with mass. Okay. The thing is that I had a ruler and I had a watch and I had a scale. Okay, and if I was in a box, I wasn't walking, but I was in a box that was moving. Okay, my ruler and my clock and my scale would all look the same to me. You guys have these same three things. You have a ruler, you have a watch, and you have a scale. The same. Okay. All right. This will make more sense later. Okay. The other thing, and I have an example too. I can't remember if it's on the next slide or if I have a blank slide coming up. The other thing, and we'll talk about why the speed of light is Mother Nature's cosmic speed limit. Nothing can go faster than the speed of light. Nothing. They're like, why not? Well, it just can't. And there are like physics reasons why not. Okay. So here's the deal, and I guess I did leave a blank piece of paper just to do this. See if I try to. We think of speeds as additive. So let me go ahead, and this is going to be totally butchered, but okay, here's me or you. Okay, and let's make this a box car, and we'll make a little kid on there. This is so terrible. And we're going to make the little kid throwing a ball at us, towards us. And we're going to make the box car moving. Right? Okay, so here's the deal. From our perspective, speeds are additive. Okay, so if the box car is moving, I don't know, it's going to sound unsafe, but say it's moving 40 miles per hour. Okay, that's very unsafe for that little kid to be up there. Okay, and let's say I don't know how fast pitchers can throw really fast, can't they? Let's say he throws it at 20 miles per hour. Is that in the same direction? Are we good with that? So does it seem like the ball is coming at us 60 miles per hour? We can actually add those two. And math works great for that. Okay? So from our perspective, then over here, we see it, because it's moving, his frame of reference is moving, and he's also throwing it in that same direction, we would say it's going 60 miles per hour. Okay? We can do that. But here's the deal, and I'll kind of do it under here. Say that we have, this is it looks like a tree, but it's supposed to be a light source. I don't know, it's shining, okay? This is shining light. That's terrible, okay? And let's say that it's moving, let's go at 0.25, 25%, or 1/4, 25% of the speed of light. C is the variable for the speed of light. Okay? And again, we're over here, and we are looking for, remember light travels in cute little packets called photons, little packets of energy? So we are looking at how fast those photons are, we can gauge how fast they're going. Okay, you would think, according to the top analogy, that we could add those two together and come up with 1.25 times the speed of light. Does that seem right? Because this, by the way, I didn't say this, but this is going the speed of light. This is how fast it's going. Speed of light, 0.25 speed of light. 1.25 speed of light. Okay? No. It doesn't work that way. It can only go the speed of light. Even they're not additive. So that's actually this is the first time for me to try to talk that through. That's what I just showed you is what this is showing you. We have two frames of reference. Okay? We have the dude stationary frame of reference. Then we have the person in this fast vehicle. Okay, notice that she is going half the speed of light. Okay. So you would think that, okay, well, first off, this shining light, okay, those little photons are reaching that guy at the speed of light. Okay. But this says now that with regard to the person in the vehicle, the speed of light coming at them, or somebody goes speed of light and it going half the speed of light, they don't split the distance between them at a speed of 1.5. They do not. It's still the speed of light. It's not additive. Okay. There's this thing called, I think this is where this fits in with Einstein's theories. Did it not work? Oh, thank you.
Well, we have a thing on it. It's just a line.
You have a what?
We have a blank on our sheet.
Oh. Speed of light. Oh, it is simultaneity. I'll put it up there. You're like, what? Yeah, because that's what I started. I think this is what that is. It comes from simultaneous. So simultaneous is simultaneity. Google it. I know. Simultaneous, simultaneity.
I love Google.
When I was getting ready for tonight's lecture, I'm like, well, that's a big word. They don't need to know. I guess I do. Okay. So actually, I have a little video to show you, and it's going to have lightning and kind of a fast-moving train, and the person in the train's got a frame of reference, and somebody outside the train has a frame of reference. And it's going to talk you through kind of simultaneity. Okay, so those were the assumptions. You're like, those are weird in and of themselves, right? But these are the three outcomes. Okay, these three outcomes of his special theory of relativity. I get his special and general theory of relativity mixed up. So here's the deal. So remember I said, my frame of reference, I'm moving, your frame of reference, you're standing still. One of the things you have is a ruler, okay? So this would be really hard for you to do. But what this says, and it's called length contraction. It's called length contraction, and here's the deal. You'd be like, I don't believe you, but you don't have to believe me. Okay, so I'm moving, you guys are standing still. I'm sitting still. The faster I move, the more this thing I'm going to describe happens. If I have my ruler, and if I have, I don't know how you guys would do this, but I have something that's 2 feet long, and I'm going like half the speed of light, okay? My ruler says 2 feet long. Oh, half the speed of light. Okay. From your perspective, and it's called length contraction, so guess what? It gets smaller. From your perspective, if you were to able to go ahead and gauge the length of my 2 feet long thing, it would be shorter. It would be shorter. Really? Really? Okay? It's crazy. It's strange.
Because of how fast you're going?
Because of how fast I'm
Okay.
going. You're like, you're just going to go with me on that.
Right,
There's
well, I mean,
three.
that's
I
the
know.
only thing I can think of that
Yeah.
makes sense, so.
Good. Yes. But it's not just because you can't gauge, it's not because your senses aren't fast enough. If you could literally use your measuring device from your frame of reference, it would measure less than 2 feet. Mine would measure 2 feet, yours would measure less than 2 feet. Okay, so that's the first of 3. Here's the second one. I'm going to actually maybe go ahead and play this little video for you, and then we'll see what we got. Seems like I need to. Decided it works better to. So to summarize, it's up here. So my joke is that, like he said, people who fly a lot are actually aging more slowly. And it's not for any reason other than time unfolds more slowly. I know.
So we all should want to be pilots.
Yeah, exactly. So my thing is like, yeah, stewardess and stuff, that's why they look so, oh. They're usually really nice, but oh. But here's the thing about stewardess, all right? The other thing, the third thing is with regard to mass. And what mass says, or that thing says, is, remember I said in your frame of reference you have 3 things. You have a clock, you have a ruler, and you have a scale. So here's the deal. Those stewardesses in their airplane going fast, right? Okay, they get on the scales and like, oh, okay, well, that looks pretty good. If you were to somehow to be able to measure their mass, how much matter they contain, not just their weight, although it would be reflected in their weight, they would have more mass. They would be more massive to you. From your perspective, from your frame of reference, they would be more massive. Okay?
On the airplane in the air.
Yes, flying fast, moving fast. It just happens to be an airplane. Yeah. But I like what they said too. So the deal is, from their perspective, if they use, I don't know how they would do this, but from their perspective, you guys are weighing less, or us guys are weighing less. Okay, so it's a mass thing. Now, the thing about this mass thing kind of gets to why nothing can go faster than the speed of light. here's the deal. And I don't know if you're familiar with like, a linear relationship or an exponential relationship like that guy just talked about. But the deal is the faster you go, the more massive you are. Okay, up to an infinity amount of mass. Okay, so basically when you approach the speed of light, you are approaching a mass of infinity. It's like, okay. So you really can't go faster than the speed of light because then you would be this, yeah. To me, that's one reason why this says that the speed of light is nature's maximum, is the fastest anything can go. Whew. Okay, see why I didn't want to cover that last week? I know. But on the review sheet, it'll kind of highlight kind of what kind of things, the outcome part I'm after, okay? So that was his special theory of relativity. Now his general theory of relativity, I think 1915, yeah, okay, 10 years later, he introduces now kind of the effect of gravity, okay? And actually, to me, it's kind of one big picture because his general theory of relativity still talks about the fabric of space and time, basically. That was introduced in one of his outcomes for his special relativity. So it's kind of one big relativity thing, I think. And this kind of highlights, the thing about Einstein is he takes extremes. He takes extremes with regard to mass and with regard to speed. So when things are very massive and or going very fast, then you need to kind of talk about Einstein's physics, really. If they're going normal speeds and normal masses, then you can talk about Newton's theories or Newton's laws of motion that we talked about before. Okay. So outcomes of Einstein's general theory of relativity. Again, time. This is kind of a fun one. And this is one that has been, I have to assume it has been done. Okay, so basically, gravity affects time. And this is what I was thinking. Now, how come it seems like time's speeding up at our house? Must be that there's, would you say more gravity? Wait, let's see. Let's look at these clocks. Yeah, this says that Earth, can you see if you compare the Earth time here is what, about 20 minutes, okay? A clock on the moon is about 22. More math. Okay. So speaking of the fabric of space and time, I'm going to play you that, see where it says bends? I'm going to go ahead and play that for you. When we were busting our chops to try to catch the solar eclipse a week ago, okay, I thought of this. Let's see what you think. I guess I need to pause this.